Ever wonder how a tiny scientific puzzle from over 100 years ago, something that stumped the smartest people on the planet, ended up being the key to the solar technology that could power our future? Well, that's exactly the story we're diving into. It's a journey from a deep quantum mystery to clean energy. So let's get into it.
So, yeah, it really all boils down to this one question. How on earth did a weird observation about light hitting metal unlock the quantum world and eventually give us things like solar panels? That's the story we're going to unpack right here.
At its core, the idea seems incredibly simple. You shine a light on a piece of metal, and if the conditions are right, it kicks out electrons. That's it. That's the photoelectric effect. Sounds pretty straightforward, right? Well, as it turns out, the details were anything but. Yeah, this seemingly simple effect turned into a massive headache for physicists back in the early 20th century. Because when they actually looked closer at what was happening, the results made absolutely no sense based on the physics they knew at the time. And it wasn't just one little weird thing. Nope. They found three totally separate characteristics of this effect that just completely contradicted what everyone thought they knew about light being a wave. It was a genuine scientific mystery.
Okay, so here's the first huge puzzle. The physics of the day said that a brighter, more intense light wave should have more energy, right? Makes sense. So it should knock out electrons with way more energy. But that's not what the experiments showed. The energy of the electrons that got kicked out only depended on the light's color, its frequency, not how bright it was. Bizarre.
And check this out. We can see the actual data that proved it. These are plots from Robert Millikan's experiments. What he did was measure the amount of voltage it took to stop the electrons in their tracks. And what he found was that a brighter light just made more electrons fly out, but it didn't make any of them faster or more energetic. The stopping voltage was exactly the same. It was completely baffling.
And the mystery just got deeper. For one, classical physics predicted that a really dim light would need some time to sort of charge up the metal before an electron could escape. But there was no time lag at all. It was instant. And even stranger, every metal had a specific cutoff color. If your light's frequency was below that line, nothing happened. You could blast it with the brightest light imaginable, and not a single electron would even budge.
So solving this was going to take a complete revolution in how we think. And it came from, you guessed it, Albert Einstein, back in 1905, with an idea that his peers thought was truly out there. In fact, get this, Robert Millikan, the very guy who would later prove Einstein was right, at first called the idea a bold, not to say reckless hypothesis. I mean, that just shows you how much this idea flew in the face of everything physicists thought they knew about light.
So what was this reckless idea? Einstein basically said, hey, what if light isn't a continuous wave at all? What if it's actually a stream of tiny, individual packets of energy? We now call these things photons, and each photon carries a specific punch of energy that's determined only by its color.
Now, to test this, Millikan built this absolutely incredible setup. He called it a machine shop in a vacuum. This wasn't some weekend project. It was a grueling, multi-year effort. And even though he started out as a skeptic, his own super precise experiments ended up proving that Einstein's wild idea was, in fact, correct. So how did this little idea of a photon solve all those massive puzzles so perfectly? Well, it all comes down to a whole new set of rules for how light and matter interact at the quantum level.
Okay, so here's how it works. Think of it like this. First, one single photon comes in and hits one single electron. Second, it's an all-or-nothing deal. The photon gives all of its energy to that electron. Third, to get out of the metal, the electron has to pay a kind of exit fee. There's an energy cost called the work function. And finally, whatever energy is left over after paying the fee becomes the electron's speed.
And just like that, this simple model solves every single puzzle. That energy versus brightness problem, a brighter light isn't stronger photons, it's just more photons. The time lag? A one-on-one collision is instantaneous. And that weird cutoff frequency? Well, that's just the exit fee. If a photon doesn't have enough energy to cover the fee, the electron is stuck. It's not going anywhere, no matter how many of those photons you throw at it.
Now, this discovery wasn't just some cool piece of physics for a textbook. It was the fundamental key that unlocked an entire world of new technology.
And you see, that totally shifted the challenge. 100 years ago, the goal was just to figure out the basic quantum rule. Today, the goal is to master that rule,
to engineer the absolute perfect materials that can use this effect with the highest possible efficiency.
And this is why it really matters to you and me. That simple interaction, one photon, one electron, is literally the tiny engine running inside every solar panel you've ever seen, every automatic door that opens for you, and every single pixel in the sensor of your digital camera.
So this brings us right to the cutting edge. The modern-day hunt for better and better solar materials has led scientists to this truly amazing new class of materials. They're called halide perovskites, and you can almost think of them as being perfectly designed for this job. They have two superpowers. They are incredibly good at absorbing sunlight, and once an electron is freed, they let it move around super easily to create a current. And trust me, that combination is extremely rare and very, very powerful. So what's their secret? Well, it all comes down to the chemical bonds, how their atoms are stuck together. This map here, it's kind of like a chart of different countries for materials based on their bonds. You've got your big ones, ionic, covalent, and metallic. But look at the perovskites, those green triangles. They're off in their own unique territory, using a rare type of bond called metavalent. And that bond is the key to everything. That unique bond gives perovskites a massive advantage. So these charts here show the energy landscape inside a material. For a typical material on the left, it's kind of hard for electrons to get free and move around. But that metavalent bond in the perovskites, on the right, it creates a kind of superhighway for electrons, making it super easy for them to grab energy from light and start flowing as electricity.
And here's the real payoff. This chart is basically a design guide for the future. It shows that by tweaking the chemical bonds, by controlling exactly how electrons are shared, scientists can precisely tune the material's properties. It's like having a blueprint to build the perfect solar material from the atoms up, completely custom designed for maximum efficiency.
I mean, it's just an incredible journey, isn't it? From a confusing observation about light to a reckless idea about a particle called a photon, all the way to a quantum blueprint for designing the future of energy. It really leaves us with a fascinating question. What else are we going to build with the quantum keys that are still out there, just waiting to be discovered?